Hello, may I audible to you?
Hi, good afternoon.
Yeah, good evening here. So, we will wait for a few minutes. Till then, if you have any doubts regarding previous sessions or lectures, you can ask. Any doubts till today, or from the lectures, or from the previous assignments? Okay, let's start a session. Meanwhile, people will join. So, welcome you all to the live session 3 on the course of the fundamental of manufacturing processes. So this is the week 3, and majorly in week 3 a portion of casting process has been covered. So we will be solving some of the previous questions of the assignments in this session. So let's get started. So let's start with the first problem. Please read the problem and try to answer in the polling section. I will try to generate the polls. After that, we will discuss. Yes, I have launched the polls. You can give your response in polling section. Yes, I have got 2 responses, and both of you are correct. So let's discuss the question. The question is, the molten metal treatment in casting process used to remove the gases dissolved in the molten metal is known as. So here melt here it is being asked that which process is used to remove the gases dissolved in the molten metal. So in the melt treatment in the melt treatment processes we have seen like these are some name of the processes which you probably have seen in the into the lectures: fluxing, degassing, alloying. And in alloying there were two different processes: addition of the grain refiners and addition of modifiers. So I will quickly talk about all these processes. uh, let's first talk about the fluxing. When we have molten material, molten metal have tendency to react with the oxygen, especially if we see aluminum. uh, Almost all the materials, they have tendency to form oxide, but uh, in aluminum we use fluxing method. Basically what we do, like here, this is the surface of the molten metal, and atmospheric oxygen, they they try to react with the molten metal, and they try to form the oxide layer on the surface of the molten metal. And because of this reaction of molten aluminum with the oxygen, uh, our metals gets consumed, or our metal start oxidizing, and because of that there is a loss of metal keeps on happening. So if somehow we try to cut the contact of atmospheric oxygen with the molten aluminum, then probably we can stop the further oxidizing of the molten metal, so that no more metal loss will take place. For that, we add some chemical reagents. uh, they are mainly the chloride and fluoride salts, and what we do, they form a protective layer. Basically they form a protective layer on the top of the molten metal, and they prevent atmospheric oxygen to react with the molten metal. And because of that, the loss of molten metal into the form of the metal oxide, it gets reduced, and we have more metal in the molten form. So uh, our loss of metal gets reduced. So that is the purpose of the fluxing. Let's try to see what is the degassing. When we have molten material, it has tendency to dissolve lots of atmospheric gases like hydrogen, oxygen, and out of these, hydrogen is the uh, hydrogen has maximum, I, I should say, solubility at the in the molten form of the metal, and we don't want those hydrogen, because during the solidification they will remain inside the material as a porosity, and they will reduce the mechanical strength of the final component which we get from the casting. So degassing is mainly used to remove the hydrogen or oxygen. So what we do here, basically, uh, we try to we try to purge some noble gas inside the molten material. We will get noble gases, so that they don't react with the molten metal. But when we try to purge inside the molten metal, then what they will do, they will try to form bubbles, and they will form the bubble, and they will try to come out of the molten material. But meanwhile, what will happen when the bubbles, when they form bubbles, then whatever the hydrogen which remains di- remains dissolved in the molten metal, they will try to diffuse with the bubbles. Basically, hydrogen which was very difficult to remove, now they will try to diffuse inside the bubble, and since bubble is going to the upwards, and finally it is coming out of the molten metal. uh, so whenever they comes out, whenever the noble gas bubble come out, they bring the hydrogen along with them, and that's how the dissolved hydrogen gets removed out of the molten material. So this is the process. This is an example of degassing process. And grain refinement and modification. Basically, we add uh, some components inside the molten material in order to enhance their mechanical properties. And we know mechanical properties mechanical properties of a material depends on its grains. So if we can control the shape and size of the grains, then we can control the mechanical properties. So these two processes, basically grain refinement and modifications, uh, in this process we try to add some grain refiners or modifiers inside the molten material to control its grain shape and size. So for example, like titanium is used as a grain refiner in the aluminum alloys, and strontium is strontium is used as a modifier in aluminum silicon alloy. Basically, their task is to control the grain shape and size. So uh, let's start looking at the options one by one. So our aim was to find out the process which is used to remove the gases. In fluxing, we tried to cut the contact of the atmospheric gases with the molten metal. So that is not a correct option. In degassing, we tried to remove the dissolved hydrogen from the molten metal. So this is the correct option, degassing. Whereas the refinement and modification processes has nothing to do with the uh, removal of gases dissolved in the molten material. So second option is the correct option. uh, I think I am clear. If any of you have doubt, please let me know, or I shall move to the next question. Okay, it seems no one has doubt, so let's move to the next question. Please have a look at the problem, try to read it, and please try to answer in the polling section. Meanwhile, I will create the poll, and after that we will discuss together. I have launched the polls. You can give your responses there. Okay, I have got the responses. Uh, it seems none of you are correct. So let's try to solve it together and see what has been asked in the question. So this question is related to the pouring technique during the casting process. So let's first draw an schematic of the casting. So in casting process we try to pour molten metal inside the mold, and let's see what is given in the first option. uh, Allow escape of air or gases present inside the cavity. Basically here we have molten metal and we are trying to pour it inside the cavity. So what happens when we first try to pour material inside the mold cavity? Then what will happen? Uh, it is obvious that first of all, when we we don't pour any metal inside the cavity, the whole cavity will be full of the air. And suppose if we when we try to pour something inside the cavity, and if air is not allowed to escape, then what will happen? Then they will remain, they will dissolve inside the molten material, and they will remain as a porosity after the solidification. Therefore it is highly desirable during the metal pouring we should give some provision to uh, to bring out the gases which is already present inside the mold cavity. Therefore when mold when sand molds are made, then there is a provision, there is a small vent is given, through which the gases which is already present inside the cavity, they come out from this side. From sprue metal will enter, and as long as metal will try to fill the cavity, the all gases which already present in the cavity, they come out. And therefore uh, our casting will be our casting will have less gaseous defect. So first option is correct. Minimize the turbulence, it is the second option. So when we are pouring the metal inside the cavity, uh, our main aim will be the whole metal should get inside the cavity without disturbing the mold walls. So as all of us have seen in the fluid mechanics, there are two types of flows: laminar flow, or let's say streamline flow, or turbulent flow. if if flow will be if metal will flow in a streamline manner, then it will smoothly go inside the mold along the sprue. After that it will go through the runner and then finally inside to the cavity. But since they are laminar, so it won't harm the mold walls. But suppose if the flow rate has been high, if flow rate was higher, then will be some turbulence in the flow would have been taken, and because of that our mold walls get eroded, or they might have gone damaged. And because of this, the final casting which we would get, it would have defect. So we don't want turbulence in the during the metal flow inside the cavity. So it is true, minimize turbulence. Let's see the third option: minimize pickup of impurities from atmosphere. Yes, it is correct. We have discussed many times, we always want uh, as minimum as impurity is possible. So we always try to pour the metal in very minimum amount of time, so that atmospheric gases, they won't comes into the contact of the molten metal, because they will try to dissolve inside it and finally they will remain as a impurity inside the casting. So our effort is to minimize the time of contact between atmospheric gases and molten metal. So third option is also correct. So here we see, during the pouring, these are things we have to keep in the mind. So all three options are correct, therefore fourth one is the right answer. So if anyone of you have doubt, please unmute yourself, or I shall move to the next question. Okay, it seems it's clear to everyone, so let's move to the next question. Please read the question. Meanwhile, I will create the polls and you can keep your responses in the polling section. Yes, I have launched the polls. Please read the question and give your response in the polling section. I have got responses from both of you, so both of you are correct. So but still let's discuss one by one for all the options. So here these are the four methods of casting. First one is the sand ball casting, which from which all of us aware of. Here the main thing is the whole mold is made up of sand. So we can see this is the portion of the mold. This is made up of sand, and here the here cavity is here. This is the cavity region. I will highlight. Before before filling the cavity, there is nothing inside the cavity. Only air will be present in the cavity before molten metal is poured inside the cavity. So that's what happened in the sand casting. But let's see what happens in the full mold casting. Okay, in full mold casting, it is very in full mold casting, the process is very similar to the sand casting. Only difference is the cavity region. Cavity region is uh, not filled up of air, but there is something else. I will try to draw with the schematics. For simplicity, I will draw so this is the sand. So all the whole red region is made up of sand, and but the cavity, this is the cavity region. Now it's not filled up of with air. Here it is filled with polystyrene foam. So there is an advantage of putting a polystyrene foam inside the cavity. When molten metal is poured, suppose molten metal is being poured inside the cavity, then what they will do? It will try to fill inside. It will try to go inside the cavity slowly. But here, what it does, it it evaporates this polystyrene foam. It gets evaporated when molten metal is poured inside the cavity, which is already filled with the polystyrene foam. So this process is used to get some more accuracy or dimensional control over the sand casting. So since here the mold is already filled up with the polystyrene foam, so the process is called full mold casting. Now let's see the next process, die casting. It is already well known to all of us. Here we will here we have a plunger and we have the molten metal, and uh, we try to put the molten metal inside the cavity. Here the orange region is the cavity, and this is the metallic die. This is the metallic die which is reusable. In the sand mold casting, the mold is not reusable, as well as the in full mold casting the mold is not reusable because they were made up of sand. But in the die casting, since the mold is made up of metallic die, therefore they can be used for many cycles. But catch is here that a plunger is being used. The task of plunger is to push the molten metal inside the cavity. So there are two advantages of uh, giving pressure with the help of the plunger. First one is the whole mold is all corners of the mold get completely filled with the molten metal. Sometimes we have very complex geometry, and if we try to fill the mold with the help of the gravity, then sometimes mold, due to lack of the fluidity of the material, it will not able to reach to the all the intricate corners of the mold. So therefore, if we try to give some pressure to the molten material, then because of pressure it will reach each and every corner of the cavity. And second advantage is uh, the solidification happens faster. uh, we know the we know that the property of any material, typically most of the material behave in same way. At the high pressure the solidification happens in lesser amount of time, so the production rate becomes faster. So there are two advantages. One is the complete filling of mold happens by applying the pressure, and another advantage is the solidification process happens faster, and therefore it increases the rate of the productivity. And here die is reusable, and that's why it is called the permanent mold casting, because mold is permanent, we can use this for many cycles. So this one is the correct option, die casting. But still we haven't seen what is the shell mold casting. I will quickly try to explain about it. Okay, it's not visible clearly. Still I will try to make you understand. Here if you can see this region, little yellow, it's little yellow and orange mixed color. This is the mold, and how this mold has been made, that is another story. We shall not go to that information how this mold has been made, but the thing is that this yellow region is the mold, and this mold is in the form of the shell. So it is not completely solid mold. or it has very less wall thickness. So this is in the form of shell, but around it has been surrounded by the sand. This brown region is the sand. uh, this shell uh, the shell is made because to enhance the accuracy as well as the dimensional control over the to in order to manufacture the complex geometry with the casting route. So cell mold casting, uh, it will be taught in this course uh, later. So there you can find the details how this shell has been made. But as of now, I just wanted to uh, focus on the sand part. Still in shell mold casting, the shell is surrounded by the sand, and therefore it is not a permanent mold. So therefore, except die casting, all other casting processes, the mold is not permanent. They uh, they can be used for one time. So for this question, die casting is the correct answer. So if there is any doubt, please ask me, or I shall move to the next question. Okay, let's move to the next question. Please read the question and try to give your response in the polling section. Meanwhile, I will create the polls. I have launched the polls. You can give your response in the polling section. Okay, I have got the both responses, uh, but they are not correct. Okay, let's try to discuss together. The question asked about it has been asked that the core is placed inside the mold cavity. So here we have core, and if you could remember the why cores are used in the casting process. So I will quickly uh, try to illustrate with an example. Hello, please all of you unmute yourself. This is how our cavity looks like. So core is something which we use to create some internal feature inside the casting. Suppose we have a casting, something like this is the final product which I am making. This is the final shape where we have here we have a hole, or let's say this is the final product which we want, which we intended to make with the help of the casting. Suppose if we now what will happen, we will try to pour molten metal inside the cavity, and it will try to fill the whole space inside the cavity region. But since core is placed, the task of core is to prevent the reach the metal in the region where it is placed. So whole mold will be filled with the molten metal, but wherever the core has been placed, it won't able to reach there, and that will, because of that, we will get a whole kind of thing. Like this is the reason of the hole, and this type of things can be made with the casting process with the help of core. So the purpose of core is to help, it helps to create internal features in the casting. So let's try to see the options. These are basically they are trying to ask what is the purpose of core inside the cavity. First one is the facilitated directional solidification. So what is a directional solidification? I will quickly try to explain. Suppose this is the cavity, these are the cavity walls, and it is filled up of molten metal. Now when molten metal comes in the contact of these cavity walls in these regions, the heat will start transferring from the molten metal to the cavity walls, and metals near the cavity wall start to solidify. So near this region solidification starts happening, and it will solidification process will keeps on proceeding from the away from the walls to the center, or solidification will move to away from the walls, and this is the process is called the uh, directional solidification. Basically we try to control the direction of solidification process. We try to solidification to start at the very uh, rear end of the mold, where we try to solidification should start from the corner of the mold and it should end near the riser, or let's say, or pouring basin. Riser or so we try to solidification should start from the corner and finally they should end near the riser or pouring basin. That is called the uh, directional solidification. Basically, we try to control the direction in which solidification should start and where it should end. So we try to control it, but our core is not performing that kind of activity. Its only purpose to create internal features. So first option is wrong. Second option is to reduce stress concentration. We know in any casting, uh, if we try to manufacture a component with very narrow features, or we have sharp corners, then these are the points where stress concentration may happen. To avoid the stress concentration, we try to give some radius. So this is the modification in the geometry we do to avoid the stress concentration, but it has nothing to do with the core material. So core doesn't help to introducing the stress concentration in the casting process. Therefore it will not be a correct option. And third option is the change the direction of liquid metal. No, suppose if you see here, the liquid metal is coming from the top. It will start from pouring basin. It will run through the sprue, and here there is a base. It is called sprue base. Here when they come, then the direction of molten metal change towards the towards the cavity region. So this is the region where the direction of molten metal gets changed, or inside the runner, when we have multiple cavities, then suppose one cavity will go from there and another cavity will go from there. So basically it is the task of runner to change the direction of the molten metal, but core has nothing to do with the changing the direction of the molten metal inside the cavity or mold. So this is also a wrong option. Here is the, let's see, the fourth option is develop the internal feature in the casting. Yes, it is correct, because already we have discussed it has cores are used to create internal features or internal holes inside the casting. So the last option is fourth option is the correct option. So I think I am clear, but still if any of you have any doubt, please let me know, we can discuss. Otherwise I shall move to the next question. I hope there is no doubt. So let's move to the next question. Please read the question. Meanwhile, I will create the polls. You can give your responses in the polling section. I have launched the polls. You can give your responses there. Okay, I have received 2 responses. So I will wait for few more seconds. Okay, okay, okay. One of you have got the correct answer. Okay, let's try to discuss it. The question the question is, the liquid to solid transformation shrinkage during casting of metals is taken care of using. So these are the some casting terminology which has been listed down as an option as a options. So let's try to discuss. First, let us draw the cooling characteristics of an metal. Let's say we have pure metal. Here we have temperature on the y-axis, at time in the x-axis. This is the molten metal temperature. This is the melting point of the metal, and this is the point of starting point of this solidification. Here solidification ends. So we started with the initially we have molten metal at a temperature which is higher than the melting point. So this is the oh, so this is the molten metal temperature which is higher than the melting point by this amount. So we do it because we want uh, we want metal should reach to all the parts of the cavity before reaching to the melting point. Therefore it needs some time. Therefore it will molten metal will get some time to reach each and every part of the cavity before it will reach to the solid it will reach to the solidification temperature. So we give some amount of extra heat, which is also known as the some superheat. And once cooling process starts, then metal starts to solidify. So this is the reason of where the molten metal converts into the starts converting into the solid metal. And once all metal gets solidified, then again we leave it for cooling to bring it to the room temperature. It's room temperature. So during this process, apart from phase change of material, there is some volumetric shrinkage also happens in whole process of the cooling from molten metal temperature to room temperature. So in this region also, here when molten metal temperature decreases to the solidification temperature, some amount of volumetric shrinkage takes place inside the molten metal. And when solidification process keeps on happening, then also some volumetric changes keeps on happening when molten metal converts into the solid metal. Also when solid metal cools down to the room temperature, then also some volumetric shrinkage happens. But we try to compensate the shrinkage effect by two methods. So for these reasons, I will drop for this reason we control the shrinkage effect by help of the riser. Shrinkage is controlled by or compensated by but for a reason here where the solid metal cools down to the room temperature, here this shrinkage effect is controlled by the pattern allowance. Shrinkage is controlled by pattern allowance. So what is being asked in the question? So I will again try to show the what riser does during the solidification process. So this is the cavity and this is called the riser. Basically our main aim was to manufacture this shape, but additionally we are giving a riser So the job of riser is when we fill the molten metal inside the mold, it will go inside the cavity, as well as the whole it will fill the riser also. When the solidification process will start, or when the temperature of molten metal will keep on decreasing, and then final till the final solidification will happen, the job of riser is to keep on supplying the extra material, which in order to maintain the shape of the casting. When solidification process will start, then the material inside the casting will start shrinking. From everywhere it will start shrinking. But if we don't supply extra material to compensate the shrinkage, then the dimension of casting will be smaller than what we wanted in the final form. So to compensate, so extra material is needed to bring inside the cavity during the process of solidification, and that extra material comes from the riser, which we have additionally made inside the mold. So that is the function of the riser, and this riser will take care of only the, the shrinkage which will happen from the molten metal temperature to till the solidification. After solidification, it cannot compensate the shrinkage which will happen because of cooling of solid metal to room temperature. Therefore, riser will be the correct option. And core already we have discussed. It is used for making internal features inside the casting. And chills and chaplets, if you have gone through the lectures, then chills are used for directional solidification. And chaplets are used to support the chills. But they don't help in compensating the shrinkage during the liquid to solid transformation. So this option will not be correct. And pattern allowances, they help the shrinkage only during the cooling of solid metal to room temperature. So it will not help to compensate the shrinkage during the liquid to solid transformation. So this option will also be a wrong option. So only correct option is the riser. So if any of you have any doubts, please ask me, or I shall move to the next question. If I am not able to make you understand at any point in the whole question, please ask. Okay, I think I am clear. So let's move to the next question. Yeah, this question is mainly from the pattern allowances. Please read the question and try to calculate what are the correct dimension after giving the pattern allowances in the dimensions. And shrinkage allowance for the steel is given 20 mm per meter. Please take a minute to understand and try to give your answer in the polling section. Meanwhile, I will create the poll. I have launched the polls. Please try to give your response in the polling section. If you are facing any difficulty in understanding the question, you can ask me. I have received one response. Okay, one more. Okay, I have received couple of responses. So one of you are correct, and uh, for others, uh, let's start solving it together. So it is given steel casting has dimensions. Dimensions are given in the millimeter, shown below in the figure. If the linear shrinkage allowance for steel is 20 mm per meter, okay, 20 mm per meter, then the dimensions of pattern will be. So final this is the final dimensions of the component which we want as a final casting. But we know we have to manufactured the pattern, and that pattern is the replica of the our final product, but its dimensions are little uh, its dimensions are not same as our final casting, so there is some variation in its dimension. So these dimensions are given to compensate the shrinkage allowance, to compensate the shrinkage during the cooling of the solid metal, which is at the higher temperature, to the room temperature, and that allowance is given 20 mm per meter, or 20 mm per 1000 mm, or 0.02 mm per mm. So I for simplification I have converted the units to mm per mm. Now let's try to look at the our final component. We have length, we have width, as well as we have height. And if we see length, comma, width and height, all are external dimensions, or they are the external feature of the component. But there is a hole which is here, whose diameter is given as a 50 mm. It is an internal feature. So we have to, if you all of you have attended the lectures, then for internal features we have to give negative shrinkage allowance, but whereas for external features we have to provide positive shrinkage allowance to the pattern. So let's start calculating what should be the dimensions of our pattern. First, let's calculate the length of the pattern. So length of the casting is given 200 mm. So let's try to calculate its length of the pattern. It would be 200 plus 200 multiplied by 0.02 mm. It will be equals to 204 mm. Let's calculate the width of the pattern. Width is given 150 mm. So dimension of to the width of the pattern will be 150 plus multiplied by 0.02 mm, which will be equals to 153 mm. Now let's calculate the height of the pattern. 100 mm. So the height of the pattern will be 100 plus 100 multiplied by 0.02 mm, which is 102 mm. And here for here, since this hole is an internal feature of the casting, so we have to give negative shrinkage allowance. So what should be the diameter of the pattern? So casting diameter is 50 mm. The diameter of pattern will be the diameter of the hole in the pattern will be 50 minus 50 into 0.02 mm, that is, that will be equals to how much? This is 1. Okay, 49 mm. So this will be the final dimension of our pattern material, which is made up of steel. So let's see which option is correct. Length 204, width 153, height 102, and diameter of internal hole is 49. So this one, third one, is the correct option. So am I clear in this question, or you need some help to understand at some point? If you're finding any difficulty to understand any point in this question, please unmute yourself, or if you haven't understood, then we shall move to the next question. Okay, it seems I am clear to everyone, so let's move to the next question. Please read the question. Meanwhile, I will create the polls. I have launched the poll. You can keep your response there. If you're finding any difficulty in understanding the question, you can ask me. I have received only one response. Okay, let's wait for 30 more seconds for others to try. Okay, let let's try to solve this question together. It the question it is being asked the characteristics of draft allowance. So I will quickly try to remind you what was the draft allowance. Uh, suppose we want to manufacture a component something like this. From the casting, then how should our mold look like? I will draw two molds. So I will draw two molds. Please write in the chat box which mold according to you will be the suitable one. One mold is something like that, and another mold is okay. Please try to understand just by the shape, because uh, the drawing which I have drawn all are having different sides. So just keeping sure. Okay, second one correct. So why second one is correct? So I will try to explain uh, why second one is basically this was the first, this was the second. I will try to explain why second one is correct, whereas the first one has some issues. If we want to manufacture the casting which have shape something like that, then we have to manufacture a pattern which should have similar shape of our final casting. So suppose if we made a pattern which looks like this. Now what we will do, we will try to fit that pattern inside. This is the sand region. Basically these are all the sand. This is the sand. If we try to put the pattern inside the sand, then what will happen? Suppose we bring the pattern and we kept here. We kept the pattern, we inside the sand, and we rammed the sand. And now what we will do, we will try to remove the pattern in order to get the cavity. So this is the pattern we have to remove. So in order to get the cavity like this, we have to remove the pattern from the molding sand. So when we try to remove this pattern, what happens practically? The walls of pattern, like these red walls, comes in the contact of the sand wall. Basically, this is the black one is the cavity wall. This black wall comes in the contact of the this red wall, and when we pull this pattern upside, then it the pattern will come in the contact of the this sand wall, and it will it will distort the cavity when we try to pull, because when we try to pull, there will be, even if there will be little vibration while removing this pattern, this two walls comes in the contact, and this sand wall get gets gets distorted with the pattern material. So this happens the because the shape was like that throughout the process of pattern removal. There are the chances when the pattern material can touch the this mold wall, and it has high tendency to distort the mold wall of the mold wall. And if our mold wall gets distorted, then the final component which we will get will also remains distorted. So what practically we used to do, we give we try to give some draft to the all vertical walls of the pattern, so that when we try to remove the pattern, it should not come into the contact of the sand. So we will modify their shape, something like that. Although I am exaggerating little, but this taper angle, this angle is very small, mostly uh, less than 3 degree. So if we modify the shape something like that, then let's see what happens. Now we have pattern something like this. Now when we try to pull this material from the molding sand, then there is very little possibility of coming any surface of this pattern to the mold material. If we lift it little, then it will come here. So this distance is increasing. So as we proceed the pattern removal process, the distance of mold wall from the pattern will keeps on increasing, whereas earlier it was not the there is high possibility of the pattern material to come in the contact of the mold wall. So there is a high chances of mold distortion in this case. High chance of mold distortion. Especially the vertical walls, they can come in the contact of the pattern material. So let's try to look the all options which are given here. The characteristics. So basically here, whatever the tapering process which we did, or the taper angle which we had given, so this is called the draft allowance. So first option is used in the vertical surfaces of the pattern. Yes, it is correct. Here this is the vertical shape, this is the vertical shape, whereas we we had we haven't done any change in this horizontal walls. We haven't given any allowance to the horizontal walls, only tapering has been done for the vertical walls. So first one is correct. External surfaces are given more allowance than that of internal surfaces. Yes, it is correct. Why? uh, Suppose this is the pattern. These are the internal walls which I am hashing with the black color. Internal walls, whereas oh, these are the external walls. So suppose we are trying to pull this pattern from the sand, then suppose our hand suppose we are trying to from pull it outside with the help of our hands, then our hands have tendency to shake either in this direction or in this direction. Suppose our hand shakes in, let's say, in right direction, then our left wall will not get distorted, whereas if we see internally, what happens? Internally this wall will come in the contact of the mold wall. This is the mold wall. So this there is and then either we will shake our pattern to the left or right, the internal walls are going to be the disturbed, whereas the external walls, they have less tendency. Suppose if our hand shakes towards the left, then right wall will be safe. If our hand shakes towards right, then left wall will be safe, but internal wall will get damaged either our hand shakes towards right or left. So there is a high tendency of distortion of internal walls with in comparison to the external walls. Therefore internal walls are given more allowance, more shrinkage allowance, sorry, draft allowance, um, whereas the external surfaces are given less uh, less allowance. But here it is written opposite. No, this is wrong. Internal surfaces should be given more allowance, internal surface should be given external surfaces should be given less allowance, internal surface should be given more allowance. And third one is that depends on the material of the pattern. Yes, it is correct. If all of you have gone through the lecture, then pattern can be made up of wood, metals and plastic, and all of have all of having different characteristics, and because of that different values of allowance given for different materials. So yes, draft allowance is a function of material. It is correct. Depends on the linear dimension of the pattern. Correct. Suppose we have length L and and suppose we have another. Okay, what I will do, I will try to explain here. Suppose we have two pattern. One is one has a small linear dimension, whereas other has a large linear dimension, and we are giving 3 degree of draft allowance. 3 degree 3 degree. Since here the linear dimension is, let's say, small l, here the linear dimension is capital L. So what is the difference we get here and what is the difference we will get here? They are not same. Let's say because of draft allowance of 3 degree, here we are getting small d, and here we are getting the change in the pattern length should be is capital D. So they are not the same, they are totally different. So capital D is, the magnitude of capital D will be much larger than the smaller d. So draft allowance is a function of the linear dimensions. I hope I was able to explain the fourth point. So it depends on the linear dimension of the pattern. It is correct. So facilitate the easy removal of the pattern from the sand mold. Yes, this is the thing which we have discussed very first. So first one is correct, third one is correct, fourth one is correct, fifth one is correct. Then correct option is first, third, fourth, fifth. Yeah, the fourth is the correct answer for this question. So I think I have explained it. So, but even if you have any doubt, please unmute yourself. You can ask me. Am I clear to everyone? Yes, you can write in the
Yes,
chat.
clear.
Okay. Thank you. Please stop me anywhere if you face any difficulty in understanding anything. So I hope I am correct. I am clear to everyone. So let's move to the next question. Please read the question. Meanwhile, I am creating the polls. I have launched the polls. You can give your responses in the polling section. I have received couple of responses. I am waiting for others. Okay, so let's try to discuss it together. So in question it is given the good collapsibility of mold sand leads to. So first thing we should understand what is the collapsibility. So basically this is the ability of mold to get collapsed. So why it is needed. So let's start discussing one by one. uh, it is one of the properties of the material to if it is one of the property of the mold which is called the collapsibility. Basically if mold can be collapsed easily, then we get several advantages which we shall discuss one by one. So we have again we have a sand mold. Collapse means to ability to deform, basically deform the mold under stress. So first option is the reduction of hot tearing. Let us see what is the hot tearing. So we have heard this term many times, but still I think we have some confusion in this term. So hot tearing, basically it's defined as the cracks formed due to the thermally induced residual stress during casting, or better I shall write it. Cracks forms due to thermally induced residual stresses during casting, or specifically during the solidification process. So what happens when let's I will try to discuss in the first figure itself. Suppose we have the mold cavity which looks like looks like this in the form of T, and when solidification will start, then metal have tendency, basically the uh, metals will try to shrink. Metals will try to shrink because of the solidification process. We have already seen, like shrinkage happens from the molten metal till the uh, till we get the casting at the room temperature. So shrinkage is the process which keeps on happening, and because of this shrinkage, I will little zoom out this thing. Because of shrinkage, material will try to, okay, I should change. Basically material will try to pull. Material will try to move away, or they will try to sink. So what happens? Because of that, there is a region of tensile strength, tensile stress, which induce during the process of the solidification. But suppose that if this shrinkage is too much and the material is being restricted, or or the material is being pulled too much, then what will happen? Then mat- material will try to pull towards the shrinkage direction, and because of that, a point will come where we will get a crack. So this type of crack, which happens because of the stresses which gets induced during the solidification process. So this kind of cracks are generated. This is called the hot tear. So based on geometry, hot tear can happen at different points in the whole casting. So I think I have explained the what is the hot tearing is. So these are the cracks formed because of the residual, because of induced residual stresses. So let's try to look at the options. And these residual stresses occurred only because the mold was not able to deform. If suppose mold was able mold was able to deform, then it would have allowed the material to flow in the direction wherever the stress is being induced. Then mold walls have been collapsed accordingly. But since it if it is not able to collapse, then 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 material will not able to flow, and therefore the cracks has been formed. So since material was not able to collapse, due to which residual stress induced, and after a certain point residual stresses becomes too high and they form the cracks. Here cracks. So these cracks are called hot tearing. So first option is it's wrong. No, correct. Good collapsibility means reduction in hot tearing. So if mold has mold have capability to collapse, then hot tearing will then we can prevent the hot tearing. So this is the correct option. Reduction of gaseous defects. It has nothing to do with the gaseous defect. Gaseous defect occurs because of the permeability of the mold, not the collapsibility of the mold. So that is the wrong option. reduction in the development of residual stress. Yes, this option is correct, because if mold can be collapsed easily, then residual stress will not induce inside the material during the solidification process. So basically they will be free from the stresses if mold is easily to collapse. So this is the correct option. We can reduce the development of residual stress if our mold is collapsible. Now it can with withstand high temperature of liquid metal. Although it is required property that mold should sustain high temperature, but it has nothing to do with the property so called collapsibility. So it is required, but it is not related with the collapsibility. So this option is not correct as far as this question is concerned. And fifth option, facilitate the easy removal of casting from the mold. Yes, once whole solidification process happens or solidification process completes, then we try to remove the final product out of mold. Then what we do for the sand casting, we try to break the mold or collapse the mold. If it is easier to break the mold, then we can remove our casting very easily. But if our mold is not easy to collapse, then we have to go for the some extra effort or extra mechanical effort in order to remove the casting from the mold. So good collapsibility will help in easy removal of the casting from the mold. That is also a correct option. So let's see what is the correct answer. First, third, fifth. Okay, the fourth one is the correct answer. So uh, if any of you have doubt, please let me know, or I shall move to the next question. Okay, no doubts. Let's move to the second last question. So it is straightforward from the slides. So please have a look, and I will try to I will create the polls. This question is from the 15th lecture. So if you have gone through the lecture, then it's very easy. I have launched the polls. You can give your response in the polling section. Okay, I have got the one response, so I am waiting for others. Yes, I have got two response and both of you are correct. Okay, let's discuss this quickly. So the first thing is we have to, there are two things given, the clay, and second thing is the good refractoriness property. So uh, if we can remember that the refractoriness is to of ability of molding sand to withstand high temperatures. Okay, so first option we have sawdust. Let's see uh, uh, what is the function of the sawdust in the casting process. Okay, okay, so I have to erase this. Yeah, sawdust is basically it is an additive material which is used to improve the collapsibility but not the refractoriness. Basically, uh, whenever uh, sawdust comes in the contact of the molten metal, then uh, it burns out, and because of that the collapsibility of the material mold gets increased. So it is very easy to collapse a mold just by very little effort. We can break it if we add the sawdust in the molding sand. So here, okay, so although sawdust is added in the molding sand, but it has nothing to do with the refractoriness property, so it is wrong. So let's see what next is the bentonite. Yeah, if you can remember the lecture, then we have sand, basically molding sand. When we try to make the mold of molding sand plus clay plus moisture, here it is in 90 to 92%. This, so maximum contribution is the sand in the mold preparation, in the sand casting. So where is the clay? Clay somewhere it is 5 to 15% if I remember it correctly, and remaining is the moisture. So there are two types of most used clay: kaolite, kaolinite, bentonite. And this kaolinite have very good refractoriness because it can withstand with very high temperature range, like 1750 to near about 1780, 7087. It is very high temperature, so it is good for the uh, casting of the material with high melting point temperature like cast iron or steel. whereas the bentonite, uh, it has uh, it has little less refractiveness because it can withstand up to only 1300 degrees Celsius, but its water absorption capacity is better. So it is used for the low melting point metal like magnesium or aluminium, whereas the stoneware stoneware is also a refractory ceramic, but it is not used for the casting. It is used for the pottery purpose. So it has uh, basically its water resistivity is very good. So the pottery is made up of the pots made up of this and this stoneware. So this is used for the making the crockeries or the pottery, but it has nothing to do with the molding. Although it is a refractory material, but it is not used for the during the casting. So we have only two refractory materials which is used to provide the good refractiveness to the mold, out of which this kaolinite, it has very high refractoriness. So whereas the bentonite is also have good refractoriness, but in comparison to both, this one is the best, kaolinite. So for this question, the third one is the correct option. So best refractoriness we will get from the this kaolinite clay. So this was the straightforward question. So let's move to the last question. Please have a look, and I will try to create the poll. You can answer your you can put your response in the polls. I have launched the polls. Please try to give your response in the polling section. It is live. If you're finding difficulty to understand the question, you can discuss here. Okay, I have got single response. Still I am waiting for others. Okay, okay, one of you have got the correct answer, so let's quickly discuss this also. So first of all, let's discuss the what is the effect of the size of the molding sand with respect to the property of the mold. So if we have coarse sand, then it has these two property: increased permeability and increased refractoriness. So here we have coarse sand and regular size. So for coarse we have to look here, and with respect to size, if we have a regular size, the regular size means they should be round, they should not be irregular. So more round, more regular. So a regular size means here round particles. So what they do, they reduce the permeability, but they increase the strength of the mold. But irregular shape, the permeability of mold gets increased, but we lose the strength. So quickly I will try to show. Suppose if we have regular size particles, then they will be there will be they will be very closely packed, very less gap will be there. Since if we see very less gaps are very small, and therefore the permeability will be less. But whereas if we have irregular particles, suppose like that, then we would have got bigger voids and irregular bigger voids, so the permeability would have been increased. So suppose that some gases will try to escape, some gas will try to cross this cross section, then it will find very difficult because it is very highly densely packed. Whereas if gases try to escape from this cross section, they can go easily there and they can come out. So therefore permeability of this irregular shape sand is higher. So let's see the question. We have coarse, we have regular. Coarse means increased permeability, but option is low permeability, so it is wrong. And coarse means increased refractoriness, so here high refractoriness is there. Let's see about the size, shape of the particle. Regular size, it means permeability will be less. A regular size means less permeability, low permeability is here. But if we see effect of coarse as well as the regular size, in coarse, since particle is coarse, because of coarseness permeability go down, and because of regular size permeability will go up. So overall effect, if we see, it will have moderate permeability. So if we see overall, the permeability will not be low, it will be not high, it will be some moderate. So keeping question in the mind, the first option will not be correct, it should be somewhere moderate permeability should be there. And if you see the all of the above, since first option is wrong, all of above cannot be correct. And this low melting point, melting point has nothing to do with the size and shape of the particle. Melting point is a function of material. If material is same, then whether it is coarse or it is fine, the melting point remains same. So size of the sand has nothing to do with the melting point, so this option is wrong. The only correct option is third one, high refractoriness. So this was all for today's session. So you can give your feedback, whether you can understand what I am discussing here, or I need some improvement, or session is going too long, I should reduce the number of questions. So whatever you feel, you can unmute yourself, or you can write in the chat. Whether all of you able to understand whatever the question I have discussed, please.
Yes.
Okay, thank you. For others, okay, thank you so much, Nagasri Nivas. So do you think I should reduce the number of question, or it's fine whether the session is going little longer? I try to solve as much I could, but if your wish session is going too long, then I can reduce the number of question less time, or it's okay.
I think it's okay.
Okay, okay, then
It's
next.
okay, sir.
Okay, then next time onwards also I will keep the number of question 10, so that we can get maximum out of this course. So okay, wish you all a very happy weekend. Please go and enjoy, and watch all the lectures of the next week, and we will meet in next Friday at the same timing. Okay, thank you so much, all of you.
Thank you. Bye.
Okay, sir.
Bye.